This video is supposed to cover some problems that we never had gone over from chapter 5. 3 problems are here, so if you want to find that work and figure out how to do these problems, I'm happy to help you with that. We'll start with 5.1, number 92. The reason this problem was selected by so many students is because many students were wondering how they could actually solve this with no calculator. And I'm going to try to show you that now. So the question is asking for us to locate any relative extrema and points of inflection, and we'll use a graphing utility to confirm our results. Okay, first, to find relative extrema, I need to take a first derivative. So I'm going to do y prime is equal to, now I need a product rule here because it's at first times second. It's a function times a function. So I'll do 2x times ln of x over 4 plus derivative of ln of x over 4, so plus x squared times, now it's going to be 1 over x over 4, which is 4 over x, times the derivative of x over 4, which is just 1/4. Now we know here that x can't be equal to 0, so let's go ahead and simplify 2x times ln of x over 4 plus, it looks like the 4's cancel and an x cancels, we're just left with x. Now, we could actually factor an x out of both terms. So if we do that, we get x parentheses 2 ln of x over 4 plus 1. Okay. I want you to note here, and I noted this earlier kind of nonchalantly, that x cannot equal 0. The reason x cannot equal 0 is because natural log cannot take on the value of x equals 0. The domain of natural log is all x greater than 0. So ln of x's domain x greater than 0, which implies that x cannot equal 0. And the reason that that is relevant is for 2 reasons. One, we divide it by an x, which means x can't be 0, or else we'd be divided by 0. And also, if I set these 2 factors equal to 0, it looks like I would actually get a 0 as a root, but again, x can't be 0. So I'm going to write down x is equal to 0. I'm going to write down x is equal to 2 ln of x over 4 plus 1. And I'm sorry, I should be writing down, x equals, so let's erase that. And let's put 0 equals, because what I did is I set each factor equal to 0. So I set this x equal to 0, and I set this part equal to 0. As I noted though, x can't equal 0, so that potential root is out. And I'm trying to solve this equation. And the way I solve that equation, I'm going to go and subtract 1. And again, this is without a calculator, so I'll subtract 1 and divide by 2 at the same time. And the way I solve for x is I have to exponentiate, which means I'm going to drop an e and make the entire equation an exponent now. So I end up having e to the negative 1/2 is equal to the e to the ln cancels, so I'm just left with x over 4, which means that x is equal to 4e to the negative 1/2. Okay, so here's the tricky part. I am supposed to plug this back in to solve for, I'm supposed to plug this back in to my first derivative to see if I have a max or a min at x equals 4e to the negative 1/2. That's kind of tricky though. So what I'm going to do is I'm going to do the second derivative test. And the reason I'll do the second derivative test is because I could use that second derivative test for extrema. I also am going to need points of inflection, so I'm going to need my second derivative anyway. So the second derivative will be done in a different color. Let's choose that one. And let's go and take the second derivative. So y double prime is equal to, now it looks like I'll just use this sign, 2 times ln of x over 4 plus, and then 2x times 4 over x times derivative of x over 4, which is 1/4, and then plus 1. And if I simplify anything here, it's 2 ln of x over 4. The x's cancel and the 4's cancel, right? So x's cancel, 4's cancel, and we'll put plus 2 plus 1, which is plus 3. So plus 3. Let's evaluate our root from the last time. So y double prime y double prime of 4e to the negative 1/2 is equal to 2 times ln of 4e to the negative 1/2 over 4 plus 3. And if you're not sure why, I'll show you why I'm doing this in just a minute. I get ln of e to the negative 1/2, which means that the ln and e cancel, and that negative half is coming down in front. So I get 2 times negative 1/2 plus 3, and that's going to be equal to 2. I have a positive second derivative, so because 2 is positive and 2 relates to my second derivative, here's what that tells me, and I need to move my face. Okay, so what that tells me is the following. I showed you these couple pictures many years ago. I showed you this one, I showed you this one. This function is concave up, and at the horizontal tangent you have a minimum. This function is concave down, and that shows you that you have a horizontal tangent at the maximum. Because I have a horizontal tangent, since the first derivative was equal to 0, because I have a horizontal tangent at 4e to the negative 1/2, I know at that value it has to either be concave up or concave down. If it was neither, then there wouldn't be an extrema there. There would just be a critical point. But I notice that 2 is positive and it's a second derivative, which means I have this case. And this tells me that at 4e to the negative 1/2, so at x equals 4e to the negative 1/2, I have a local max. Now if I want to find the actual value, I would need to plug in 4e to the negative 1/2. So I'm going to erase this below the domain part. I'll make some room here. Okay, so 4e to the negative 1/2, because it does say find the extrema, which means I need to actually find the value of the extrema. And 4e to the negative 1/2 plugged in is going to undoubtedly look ugly. It's going to be 16e to the negative 1 times, again, we're going to plug in 4e to the negative 1/2 here, and the 4's are going to cancel, and we'll just get times negative 1/2, which is going to be negative 8e to the negative 1. So our local max is going to be 4e to the negative 1/2 and negative 8e to the negative 1. And that's how you would solve this problem with no calculator. That's for the first part. To find the point of inflection, so I already solved for y double prime, so I'll continue that work down here. And let's go and just go, this is going to be horrible, I'm sorry. Okay, so let's go down here and let's do 2 ln x over 4 plus 3. ln of x over 4 plus 3. Let's set that equal to 0 to see if we have a point of inflection. And if I'm solving, I'm moving the 3 over, I'm dividing by 2, and I'm exponentiating. So I'm going to get x over 4 is equal to e to the negative 3 over 2. I subtracted the 3, I divided by 2, and I raised both sides to the e to the something, e to this equation. That's how I got e to the negative 3 halves, and e to the ln canceled out to get x over 4. Multiplying, I get x is equal to 4e to the negative 3 halves. And again, I could plug that into the second derivative and do a line test here to see. to see if I get a sign change in the second derivative. So just as a reminder, the point of inflection must have a sign change in concavity, must have a sign change for second derivative. Okay, so that's how we're going to find it. Now that's what a point of inflection is. How we're going to find it is going to be, we could do two ways. We could make a line test, but if this is no calculus, I really have no idea what the value of 4e to the negative 3 halves is. Like I could approximate that, but it's going to be a long process. I could repeat that idea of the second derivative test, though, and do a third derivative, plug in 4e to the negative 3 halves. Well, actually, hold on, let me think about this. Can't do that. We're going to have to do a line test. Let's do a line test. Ugh, this is going to suck. Okay, so here is 4e to the negative 3 halves, and I'm sorry I talked out loud about the wrong answer. I got f double prime as this line test. I need test numbers on the left and the right. Oh, this won't be terrible. So let's test 1. Because here's why I'm thinking 1 is a good reason. If I'm taking 4 and I'm multiplying by e to the anything, that just means I'm going to get a positive number out. And a 4 times a positive number, now I'm thinking, hold on. Okay, I had to think about that for a second. So if I want to plug a number in, I could plug in a number like 3e to the negative 3 halves, or 2e to the negative 3 halves, or 1e to the negative 3 halves. I can't plug in 0e, because again, x can't be equal to 0, so let's just do 2e. So if I plug in 2 ln of 2e to the negative 3 halves over 4 plus 3, let's see what this sign is. And while we're at it, let's also do 8, because I'll test 8e to the negative 3 halves for the other side. So let's do 8. Let's do this one. So 2 times ln of 8e to the negative 3 halves. 4 plus 3. And let's see what we end up getting out here. So this one is going to be 2 ln of e to the negative 3 halves over 2 plus 3. This other one is going to be equal to 2 times ln of 2e to the negative 3 halves plus 3. And that ln of a half and 2 is not helpful, so let's get rid of that guy. Using laws of exponents, we get 2 times ln of e to the negative 3 halves minus ln of 2 plus 3. And let's just clean this up now. So that means we're going to get the negative 3 halves is going to come down in front. And that means we can do ln of e, which is 1. And 2 times negative 3 halves is minus 3 minus ln of 2. And then plus 3, which is equal to negative ln of 2, which is less than 0. So our sign value is negative. And for this other one, if I break that up in the same way, and actually, I made a small mistake here. There should be a minus 2 here since I'm distributing the 2, but it's not going to change the outcome. We still have a much larger negative number. For the other one, if I do the same exact process and a little bit quicker, I get 2 ln of 2 minus 2 times negative times 3 over 2 plus 3. And this is going to leave me with 2 ln of 2, which is a positive number. And I do get a sign change at 4e to the negative 3 halves, which means I have a point of inflection. A point of inflection occurs when there's a sign change in f double prime. So to find the actual point of inflection, I need to plug this value back into the top. So plugging 4e to the negative 3 halves, there's no room for this. Plugging 4e to the negative 3 halves here, and I'm going to erase the first derivative here. Bye. So plugging 4e to the negative 3 halves out. Was I using purple? So, it's purple. Okay. I would do y of 4e to the negative 3 halves. And that's going to be equal to 16. E to the negative 3 halves squared is going to be to the negative third. Times ln of 4. So the 4's cancel. The e, natural log of e cancels. I'm just left with the negative 3 over 2 because that comes down the front. Which means now this is going to be a 8 times negative 3, which is a negative 24. E to the negative 3. So my point of inflection is going to be 4e to the negative 3 halves, comma, don't die on me now, comma, negative 24, e to the negative 3, and we're going to skip the graphing calculator part. And I know this is a lot of work. This is how I would solve the problem without a calculator. It's a tough problem, and it makes sense as to why you guys asked about it. Let's go to the next one. Okay, so we're going to find the area of the region bounded by the graphs of the equations. Okay, so this one isn't bad. They already give us what the integral is going to be set up as, and we need an integral for area, so that requires an integral. We'll do an integral from x equals 0 to x equals pi of 3 to the cosine of x times sine of x dx. I also want to note here something else. The integral of a to the x dx is equal to the integral of a to the x over ln of a plus c. So here, let's go and do a u equals. I'm going to need a u equals on the exponent, so u equals cosine of x. du is equal to negative sine of x dx, which means I'm going to have to compensate this integral for a negative. And the other thing I'm going to have to do, and we missed points on this on the test, is change my x's that were 0 and pi to u's. Now, some students have found a workaround where they find the antiderivative in terms of u and then just plug the x's back in again. That's fine, but I'm going to tell you I've definitely seen multiple choice questions on the AP test that have the limits of integration change. It's a skill you need to know. So let's go and do u of 0. Cosine of 0 is 1. Let's do u of pi. U of pi is negative 1. So we're going to get a new integral now from u equals 1 because the 0 was with the 1. And let's go ahead and do the other one. U of pi is negative 1. So u equals negative 1. And then let's plug in our 3 still staying the same. This is now raised to the u. We need a negative in front because we have a negative sine x, and sine x dx was equal to a negative du. And that looks a lot simpler. This is equal to negative 3 to the u over ln of 3. And we are evaluating this from u equals 1 to u equals negative 1. Please keep in mind something else here. I don't have to go back to x equals. The reason I don't have to go back to x equals is because a definite integral is just going to get me a number. I would have to go back to x if I was just getting an antiderivative and no number. So an indefinite integral, you would go back to x. A definite integral, if you want to get the number, and who cares if it's in terms of u or x. So we'll finally get, plugging in top minus bottom, negative 3 over ln of 3, but this is to the negative 1, minus, or rather plus, minus a negative 3, to the first over ln of 3. And there's not much you can do here. We'll have 1 over ln of 3 times, that's a 3, that's a minus 1/3. 8/3. So 8 over 3 times ln of 3. Or if you wanted to do 8, because again, I want you to be aware on a homework problem of how many different ways you could rewrite this. We could also get 8 over ln of 27. Any one of those answers would have been fine. Any one of these would have been fine. And for the last problem, we tried this problem in class a little bit. It's going to be a little bit weird. I'm going to call this side A, I'm going to call this side B. And the idea is if I want to maximize the angle theta, I want to minimize the value of C from here. Like I want C to be in the perfect spot such that theta is actually a little bit, is as big as possible. I know theta can't be as big as possible here in this line, because when I try to connect that, theta is a little bit smaller. Similarly, if I tried to do theta over here with C over here, theta is also more narrow, so I kind of need it more, maybe even in the center is ideal. But let's see here. When I maximize theta, when I make this angle as big as possible, I'm making A as small as possible and B as small as possible. So the height here is 2 for this triangle. The length here is C. And for the green triangle, the height here is also 2, but the length here is 4 minus C. And since these are both right triangles, I can do some right angle trig, and I can get the tangent of A is equal to 2 over C, and the tangent of B is equal to 2 over 4 minus C. And what I want is I know that the tangent of A, I'm thinking here for a second. I want A to be as small as possible and B to be as small as possible. So a function in terms of A and B is equal to the tangent of 2 alpha. The tangent of A plus the tangent of B. But again, I want these angles to be as small as possible. So since I want these angles to be as small as possible, I actually want to take the derivative. Now, the derivative is going to be equal to the same thing, since tangent of A and tangent of B is equal to 2 over C plus 2 over 4 minus C, minimizing A and B also minimizes C. And minimizing C maximizes theta. So let's take a derivative here. Then f prime, so this is, by the way, is now f of C, since we got rid of our a's and b's. So now if we take f prime of C, we get, so remember 2 over C is 2C to the negative first. We get negative 2 over C squared. And for this one, it's going to be 2 times 4 minus C to the negative 1. So we need a chain rule. And this is going to be plus a negative 2 times 4 minus C to the negative 2 times the derivative of the inside, a negative 1. And we end up getting negative 2 over C squared plus 2 over 4 minus C squared. Please note C cannot equal 0, because if C was equal to 0, we would have the smallest angle possible, the smallest angle theta possible. So let's set f prime of C equals 0, because we want to again find that value of C that minimizes this. So if we set C equal f prime of C equals 0, we get 2 over C squared is equal to 2 over 4 minus C squared. And this just implies that C squared is equal to 4 minus C squared, By taking the square roots, we do technically get plus and minus, but we only want c to be positive, so we end up getting c is equal to 4 minus c. And solving this, c is equal to 2. And doing my line test, I want to make sure I get a sign change from negative to positive. So for c equals 2, let's plug 1 back in, and I get a negative 2, so if c is equal to 1, equals to 1, I get a negative 2 plus 2 over 4 minus 1 is 3, so 2 over 9. That's definitely a negative number. If I go to the positive side, like c is equal to 3, or 4, let's do 4. So 4 squared is 16, so I get a negative 1/8. And then plus 4 minus 4, oh no, c can't be 4. Dang it. That's true. Can't be it. Alright, let's try again. And this is c equal to 3. That should be better. That means I'm going to get negative 2 over 9. Plus 4 minus 2 is 2. 2 squared is 4, so I get plus a half. And a half is bigger than negative 2/9, so that's great. Which is equal to a positive number. And I do indeed have a minimum at c equals 2. So a min at c equals 2, because f prime of c changes from a negative to a positive. Okay, let's go back and answer the question. The question is asking for find the value of c that maximizes the angle. And when we minimize c, when we minimize a and b, we minimize c. When we minimize c, we maximize theta. So the answer is c is equal to 2. Okay, and those are the 3 questions that I wanted to answer for you. Hope these help. Thanks for watching, guys.